So these kind of points, the intersection, what do you think about the dimension of this manifold? One, right? Just a line. And you can get from here, why? Because let's see the Jacobian of these f's is please differentiate every f with respect to x, y, and z. This is super easy with respect to x is 1, 1, 1, right? This guy is 2x, 2y, and 0 with respect to z, okay? So, obviously, they will be always independent, except if x and y is 0, this guy will vanish, so it's not a new information, right? So, so this is rank 2, except for the points where x and y equals 0, which is the z-axis. But actually, the points where x and y equals 0, they don't satisfy my level set, so they are not on the set. So the set M is every x. Come on, man. This was not so convenient. The set where every x, y, and z belongs to R3 and satisfying these two equations, we will have this as rank 2 always, right? So every x, y, and z in R3 is such that F1 is 1 and F2 is also 1. Over this set, we have F1 and F2 rank 2, right, on M. So it's as if you have 3 coordinates, x, y, and z, but you have 2 constraints, right? So how many degrees of freedom you're left with? It's just only 1 degree of freedom. So actually M is a one-dimensional manifold. If you want to prove it rigorously or from the basic definition, can you provide me with charts? Let's suggest some charts. The point is, we will have some neighborhood, U1 for example. And take my point, take my word now that this is x, y, and z, I mean in R3, or in actually M, such that, let's say y is greater than 0, okay? Let's take this open set. So I need projection from x, y, z. You need to project and give me something. So phi is a map from R3, or sorry, from U1 to what? This is what? R, right? Because it's one-dimensional thing. So you project on anything. Project on some variable, you have x, y, z, project on, say, x, and then the inverse is how to recover y and z from x through the equations, right? That's it. So phi 1 will take x and should give me x, y, and z from the equations. So here's x. What's y? Well, I can get y from this equation, so it's square root 1 minus x squared. But you will encounter the challenge that it can be positive or negative the square root. So this is why we confine to the positive solution, and we will need to cover the negative solution later on. So this is square root 1 minus x squared. And I can get z from the other equation, right? It's 1 minus x minus y. So this is 1 minus x, and y in terms of x is square root 1 minus x squared. So this is one covering. Okay? And then you need to do another chart, right? And maybe a third or fourth chart, or if you want to do the stereographic projection, you can do stereographic projection. Or do it in any other way. This is just a straightforward way. Project on one of the variables and get the other ones from the equations. Okay? Any question about that? So we'll move now to okay, we should now be very familiar and very comfortable with the concept of a manifold. We really know what we mean by a manifold, right? So by a manifold, when I tell you M is a manifold, so this is M, I immediately know that for any point, I have this guy. I have a map to a flat space, Rn. This is Mn, n-dimensional map. And I have phi inverse, right? For any neighborhood, and we can have overlap. So we want to do calculus on a manifold. What do you mean by calculus? We want to do differentiation on a manifold. So we will try to define differentiable maps. A function f from R to R is differentiable when? Differentiable if what? If what? If the limit, differentiable at x, say, right? F of x plus h minus f of x divided by h, limit as h goes to 0. Can we do the same definition for a manifold? Let's see. The function is differentiable at this point. F of x, first of all, f, so function f that takes a point in the manifold to real. At any point in the manifold gives you a real number. So something like that. This is f, this is the real number. Like the temperature of the earth. At any point on the earth, give me the point, I give you the temperature. It's a number, right? Okay. Now, this function is differentiable. I want to define differentiability. Just definition. Let's see, how can we define differentiability? This is differentiable. If what? What condition can you put? Can you put this condition? What we are doing here, at a point we perturb the point. What do you mean perturb? I cannot even add on the manifold. I cannot add x plus h. Addition is not defined. This is a very vague space. And if you add, if it's in an ambient space, high dimension ambient space, if you add, you will get a point maybe outside the manifold, right? If you are in 2 points on the circle, this is S1, and I add this point, that point. How are you going to add? How are you going to define addition? If you add in the sense that they are points in R2, then if you add these two vectors actually, you will get this guy. You'll get a point here, right? So it's not in the manifold. Addition is not generally defined. I cannot add. And this is another form of addition, right? Subtraction. And even if I can add, man, division is something crazy. I cannot divide. Cannot divide by a point in the manifold. This is completely out of the picture here. So how can we define differentiability? And actually, the simplicity of the definition that I'm going to show you will show you that, you know, it's as if we're cheating. It's as if everything is right. In the sense, let's see. Can you look at this picture and give me an idea how to define f, the differentiability of f? What about the following? If I compose f with phi inverse, so I have phi inverse, this is a manifold. Whenever you're saying a manifold, I'm already given this thing, right? So it's as if, whenever you say this is a Euclidean space, I already know that I can add. Here I already know that I have this map that maps any point in the manifold to a flat space and back. So if I have this map and compose it with f, phi inverse f, so for any chart, for any local chart, u and phi, the map f composed with phi inverse. This is a map from where to where? From Rn to R. Wow, this is a map that, you know, I'm very comfortable with. And I can define its differentiability. Is differential. So it's indeed the flattening. I flatten the manifold into flat space. Indeed, this flattening that allowed me to define calculus. I will do the calculus always by mapping here. Okay? So this mapping is very important in the sense I cannot do things on the manifold. I will go here and always do the calculus. So coming from here to there, it's just a map from Rn to R. I can define differentiability, for example, just go and compute partial derivatives, they are continuous. I think this is a sufficient condition. Compute your partial derivatives. So,
Professor,
yeah.
I can get where did we reach that F acting on phi inverse get us from Rn to R? The last line.
Yeah. So, first of all, did you understand this statement?